Hello friends. So we'll continue our discussion on consistent deformation method for single span problem. We were discussing a fixed end beam. So we already discussed how to analyze a fixed end beam using consistent deformation method if there is a UDL all over the span or if there is a eccentrically loaded point load. We'll continue our discussion with the moment now. If there is a beam, fixed end beam, which is subjected to a concentrated moment at any distance, say A from one end and B from other end. So definitely because of this moment, if these fixed ends are not there, then it will try to deform like this, right? It will try to rotate this portion anti-clockwise and this portion also this portion clockwise. So this moment, fixed end moment, it won't allow it to rotate, right? If it is simple support, then it will rotate like this, but since we have this fixed end, so fixed end won't allow the rotation. So this rotation will be resisted by the moment. So since this end is like trying to rotate in counterclockwise direction, so this moment will be in clockwise direction, whereas at this end, this end is also trying to rotate about counterclockwise direction. So this moment will develop in clockwise direction. So this is the only change in like previous what we have done, and here since now the directions are changed, we need to be careful in calculation. So again, this problem has static indeterminacy of 2. So considering MA, FB and MFBA as a redundant moment, we can release this beam. So we have to remove this two moment, then like you'll get this released beam, and then actual load M is acting, M moment is acting on the beam. Now again, this total span you assume like L, this total is like L, and this from A support it is A, and from B support it is B distance, right? So now this is the released beam which has external load as a moment M, concentrated moment M, right? And then we'll be applying the fixed end moment individually, right? Then using consistency condition, what we tells the addition of this 3 rotation must be equal to the rotation in actual beam. So in actual beam there is no rotation, so addition of this 3 should also be 0. But now this change is there, right, compared to like previous cases. So the consistency conditions will be theta A, like theta A, I am assuming like here counterclockwise rotation positive, right? So theta A positive, then this rotation, this moment MFAB, it will try to resist this rotation, that will rotate this part in clockwise direction. So this moment will be clockwise, and since we have assumed like here anti-clockwise positive, so clockwise will be negative. That's how minus M theta A1. But when you apply this moment here MFBA, this MFBA will rotate this beam in, at this end it will rotate the beam in clockwise direction. So this clockwise direction rotation here, it will cause anti-clockwise rotation. So this anti-clockwise, again anti-clockwise we assume positive, that's how it will be positive theta A2. Similarly, now here also we can write down like algebraic sum of this 3 should be 0. Since these 2 rotations are same, so we'll use positive sign for this 2, and this is opposite to this 2 rotations, so we can use negative sign, right? So vice versa you can do, no issue. So like theta A plus theta B1, these 2 are in same direction, both are in anti-clockwise direction, so positive, and then this like we are assuming in opposite direction, so minus. No doubt, like even if you assume clockwise or anti-clockwise as a positive and clockwise negative, then also you'll get the same equation, right? So this is the consistency equation. So there is a slight change here in the consistency equation what we have discussed previously. So previously this 2 used to get negative, this 2 used to get negative, but now one part is positive here. So we need to be careful about the sign convention. Now the procedure broadly it is same again. So now we have to calculate thetas. So we'll calculate theta A, theta B, like we'll use conjugate beam method. So like now we are applying this moment M. So the reaction, if you calculate, this reaction will be upward M by L, and this reaction will be downward M by L. Now we will be plotting bending moment diagram. So this bending moment diagram will be like from this end, if you try to calculate, this is upward force. So like this is going to be upward, this end is going to up. So at any x distance, what will be the moment? This force into this distance. So at point B from this end, it will be mb by L. So this is like a reaction, and then this we are multiplying with the distance. So that's how it will be mb by L. Similarly, and this is like a positive moment or sagging moment, whereas at other end, if you try to see, this is coming down, right? So this moment will be negative moment. So like if you try to calculate moment at any distance x, then it will be ml into x, and then maximum up to a point it will be MAL, or otherwise like you can try to calculate at each point. Then you consider this one, there is a like concentrated moment, so there will be abrupt change. Even if you calculate moment at all the point from this end, then also you will get the same bending moment diagram. But I am not going to discuss more detail about the bending moment diagram, since you know that how to plot bending moment diagram. Now this is important part, this you should remember, because I told you that for this problem sign conventions are very important. If you make a mistake, then you won't get the answer. So like if shear force of conjugate beam is positive, then rotation of the beam is clockwise. So like shear force of conjugate beam is positive, then the rotation of the beam is clockwise, and shear force of conjugate beam is negative, then rotation of the beam is anti-clockwise. So if you remember, for normal problem, if we have this load, then this beam will rotate like this, right? So like if you try to plot bending moment diagram, it will be like look like this, and like here you understand, this is like say conjugate beam of this problem, this is M by EI load, then this reaction is upward. So shear force here is positive, because when we calculate left to right, that time upward force we assume positive. So this positive force, what it indicate? This rotation. So this rotation is clockwise rotation, whereas at other end, if you can see, this force is also upward. But when we calculate shear force from left to right, sorry, right to left, that time upward force we assume negative. So negative force indicate this rotation. So this rotation is anti-clockwise. So that is what is mentioned here. So shear force of conjugate beam is positive, the rotation in the beam is clockwise. So like if you get negative shear force here, it indicates like anti-clockwise rotation, and if we get positive shear force, then it indicate clockwise rotation. So this you need to be remember. Now so like again theta A of this real problem or released beam is equal to shear force of conjugate beam. So shear force of this conjugate beam. So now we have to calculate, we know that the shear force at a point will be this reaction. So no doubt you can assume it upward or you may assume it downward. So I'm assuming it downward, since these two forces are equal in opposite. So they'll try to rotate beam in like this. These two forces will try to rotate beam like this. So this two reaction will oppose this to this rotation. That's how I have assumed it downward, and this is upward. Even if you assume upward, then also you'll get the same answer. Since we know that like if we assume like opposite side, then we get minus sign in the answer. But since like I am assuming downward, so it will be like a positive answer. So now the theta A is equal to shear force at A of conjugate beam, and then we have to calculate VA. So this VA is equal to, to calculate this VA, we will be taking moment about B point. So first, due to VA into this L distance, so VA dash into L distance, this will cause, like in case of reaction calculation, we are free to assume like any sign convention, but whatever the sign convention we assume, that we have to follow. So I am assuming this anti-clockwise positive, clockwise negative rotation. So there are so many clockwise, anti-clockwise, so you have to remember there are reaction calculation, there are bending moment like this calculation. So whenever we do this calculation, that time we will be following sign convention of sagging and hogging, that is sagging is positive and hogging moment is negative. But for reaction calculation, you are free to assume either clockwise, anti-clockwise, positive or negative. So here I am assuming this anti-clockwise moment positive and this anti-clockwise clockwise moment as negative. So therefore VA dash into L, VA dash into L. So we are taking moment about this B point. So this distance into this moment. Now again due to this one, so this is opposite in direction, right? So it should be minus. So like what will be moment due to this triangle load? Then area of this triangle load multiplied by centroidal distance. So area of this triangle will be, so this distance is A. So like CG of this portion will lie A by 3 from this end. From here it will be A by 3, and from this end it will be 2A by 3. So now we have to calculate moment due to this triangular portion. So area of this triangle will represent the total load. So load into distance. So load will be 1/2 base into height. So this height is equal to MA by EI, right? And now then this portion, it is like again it will cause anti-clockwise moment like this reaction. So it will be positive. So positive, again triangular load, area of the triangular load multiplied by centroidal distance. So for this portion, how much centroidal distance will be? This distance B plus A by 3. So this much is the centroidal distance from B point. That's how, like area of triangle multiplied by B plus A by 3. And for this portion, it is like a triangular load 1/2 base into height. Height is MB by EI into L into distance. Now this distance, now since total is B, from this side it will be 2B by 3. So then this is the equation that we get. Now we'll keep this VA dash on one side, we'll bring all other terms on other side. So this positive will become negative there, sorry, this negative become positive there, and this positive become negative. So this L is coming from here, this portion is like this one. Now it was negative here, so here it will be positive on right hand side. So this term on left hand side, since it is positive, so if you go on right hand side, so it will be negative. So now again what we can do, we can take like M EI into L, sorry, here there should be L, there should be L, right, because this L is there. So this L, so M E I L, and this, if you carefully see, this 3 and 2 together become 6. So this part I am taking out, and already L is there. So that's how this become M by 6 EI into L square. So and then remaining term inside the bracket will be A square in bracket. So this A square, this 2A together become A square, and then this portion, remaining portion we have taken out. So 3B plus A minus, now this B and this B become B square. Again this B is there, and this 2, we are not cancel this 2 because we want to make it like a 3 into 2 6. So we have taken it outside. So this 2B B and this B, so that's how it is 2B cube. Now this answer we got with this sign convention, where we have assumed it is downward. So if you consider it upward, then what you'll get is 2B cube minus this term. But since like this is the answer we are getting with downward notation. Now very important, the theta A is equal to shear force at a point. So if you calculate shear force at a point, then this is downward force. And when we calculate from left to right, that time downward force we consider negative. That means negative of this force is the shear force at this point. Right? Negative of this value is the shear force at this point, and that is the rotation. So this much negative shear force, negative rotation, negative shear force indicate rotation of the beam is in anti-clockwise direction. So this is what we have assumed. Like here we have assumed that this rotation is in anti-clockwise direction, right? So this is like very much match with this one. So you need to be careful. Again, I'm telling, if you make a mistake in sign convention, then you won't get the result. So by chance, if you are not getting the result, then you need to be careful about the sign convention. So that is what, like here this is what rotation we have assumed, and again with the equation we got the same answer. Now then negative of this one, so I'm bringing this minus sign inside. So theta A is equal to m, I mean this will go inside, so this become positive and this become negative. So this much is anti-clockwise rotation, right? This is what, like this is one very important equation. This much is the anti-clockwise rotation. This is negative. See, we are taking the value of this force and the direction of this one. So this is downward. This is the downward force. So that's how it is negative. And negative shear force indicates anti-clockwise rotation. So this much theta A will rotate in anti-clockwise direction. Right? So next we will calculate theta B. So we'll calculate theta B. So theta B is equal to shear force at B point of conjugate beam. I hope it is visible. Yep. So like we have to calculate this shear force at this point of conjugate beam. So now we will be taking moment about point A and will equate to 0. So it is exactly same procedure. First say due to this VB dash, which will be equal to force into distance. So force is VB dash multiplied by this distance, and then due to this triangular portion, this triangular portion. So again here we are assuming like anti-clockwise positive moment, clockwise negative moment. So this moment will be negative, this will be positive, this will be positive. So then therefore VB dash into L minus, since it will cause now clockwise moment, minus area into distance. So area of this triangle is 1/2. This is the load, which is equal to area of this triangle. So which is equal to 1/2 base into height. Height is MB by L EI into L. Right, and then distance. Now we have to consider this distance. So this distance will be equal to this A plus B by 3. A plus B by 3 plus. Now this will cause anti-clockwise moment. So that's a 1/2 A. This is again area of the triangle, which will be the total load into distance. So this distance will be 2A by 3. So 2A by 3, and this should be equal to 0. So we are like using this condition of equilibrium on conjugate beam, and we got this equation. So now again we'll rearrange the term, and if you rearrange the term, so again this side is negative. So if you go on right hand side, then if this term goes on right hand side, then it will be positive. Just a minute. Okay. So if this side goes on like right hand side, then it will be a positive moment, and this will be like a negative. Since it is already positive, so it will be a negative. And this L we are bringing, so here we are multiplying it, so it will go in denominator on right hand side. So that's how we can calculate VB dash. So again we can bring out this M, E, I, L and 3 multiplied by 6 outside. So M 6 EI L square. This L and this L become L square. Now like to take this 3 outside, we have to multiply 3 here and then divide it by 3. That's how this become 3a plus b, this bracket, and this 2b become b square minus like here we are taking m outside, e outside, I outside, L outside, and this together 6 we are taking outside. So what remain inside is a, and this 2a. So that's how it become 2a cube, right? And then this force, like if you see, we have assumed it upward, right? So since it is upward, that means the shear force will be negative shear force. Why? Because when we calculate shear force from right to left, that time upward we assume negative. So that's how theta b is equal to shear force at b point, which will be equal to minus vb, right? Minus vb, because this value we got with the upward sign, right? So if you consider downward, then it will be 2a minus this portion, but that time this force will be positive, so you will get same thing. So like we'll take minus of vb, and again this minus vb minus shear force indicate, minus negative shear force indicate anti-clockwise rotation. So again if you see, check here, this rotation is anti-clockwise rotation, right? This is like, that is what we have assumed. Because of this it will rotate like this, and that is true. So this will be anti-clockwise rotation. So again we will substitute this value of vb dash here, and if you again rearrange the term, this is what will get the value of vb dash. This is very important regarding the sign convention. Again I am telling, if you make a mistake in sign convention calculation, then definitely your answer won't come. So then here it is anti-clockwise rotation. Since this shear force was negative in conjugate beam, here also shear force at B point was negative in conjugate beam. That's how this rotation is also anti-clockwise, right? Now this is like like you have to calculate. Again after this, what we did is we calculated this theta a1, theta b1, theta a2, theta b2, but this calculation it's almost same. Only difference what it will be, previously we used to assume this moment mf a b like this, and then we solve the problem. But then even if you use conjugate beam method, that time we got this triangle. If you remember, this was upward force, right? That's how we calculated. But this time it will be downward force, since this moment is in opposite direction, right? That much will be the change, but the value will remain same. So we are not doing all that calculation, since we have already done. Or if you want, you can like refer previous two like videos. So now theta a is equal to mf ab into L by 3 ER, but this is in clockwise rotation, right? This is in clockwise direction. And then at other end, theta b1 is mf ab into L by 6 ER in anti-clockwise direction. So this result you can easily get using conjugate beam method. So I am not doing that, since we have already done it 2-3 times in previous lectures. Again now at again we have to calculate theta a2 and theta b2. Now here we will be applying this clockwise moment mf ba. So if you apply this moment mf ba, then you will get the rotation here is like clockwise rotation. Here it will be anti-clockwise rotation, right? Now we will be using this consistent condition. So we'll substitute value of theta a1, theta a2 in the equation 1 and 2. Equation 1 and 2 is this equation, right? We'll substitute value in this like consistency condition. So if you substitute this value in consistency condition, then what equation we are getting is this equation. Simply it is same, again we have done previously also, but only difference will be like negative sign will come now, right? So in previous case we got this answer with the positive, like this positive and theta, but this time one is negative and here it is negative. So again rearrange the term, so like you can see that difference. Otherwise in previous problem it was plus, this is also plus, but now this, in this case, this one is negative, this one is negative, right? So this is the equation we got. Now we'll substitute value of theta A and theta B. Okay, so like if we substitute value of theta A and theta B, so like I have substituted theta A, this portion is like as it is, this, oh sorry, this is like since I have to calculate MFAB and MFBA, I have brought this term on other side and this theta A on the right hand side, and I have substituted value of theta A. So theta A is m by 6ei L square 2 in bracket 2b cube minus a square 3b plus a. This equation we have already like derived. So this equation, this is the theta A value I have substituted here. So m 6ei L square 2b cube minus a cube in bracket 3b plus a. So same thing I have substituted here. Again now I will substitute theta b as well, and like ninth equation, this equation, like we'll be substituting theta b, but again I am bringing this theta b on right hand side and this term on left hand side. So I have put this on left hand side and then I have substituted theta b. Again this 6ei and this 6ei will get cancelled, right? So this portion we have already got it like from here, right? This part. So this 6ei will get cancelled, this 6ei will get cancelled. That's how we have took it out like a 6, right? And then this L also you can bring on this side, right? If you bring this L on this side, this will be L cube term. So outside it will be m by L cube if you bring it on this side, right? Now what we'll do, we'll bring it on this side and then we'll take it twice, because since I want to cancel some term, so that I want to find out equation of MFAB and MFBA. So what I'll do, these two equations I have, like if you remember last time we subtracted, here we have to add, since already we have negative sign. So what I'll do, I'll multiply this equation with 2, and then since like here there will be 2, and then I'll add them. So this is minus, this is plus, so they'll cancel each other. So that is what, like adding twice of equation 2, so you multiply 2 on both sides, so that won't change the equation. So we are multiplying this on both sides 2, and then we are adding to equation 12. So this is what like here if you multiply by 2, again I have brought this L on this side, so it become L cube. Now on left hand side you will get only this term, right? So we are multiplying by 2 now. So like here it will be 4 MFAB, then here it will be 2 MFAB, since we are multiplying 2 to this whole bracket, is equal to, we have multiplied 2 to this portion, so it will be 2. And then on this side we are not multiplying by anything, so as it is it will come. Now if you add this, this is negative, this is positive, so they'll cancel each other. This is like 4 MFAB minus, so this is minus, so it will be 3 MFAB. So this part is okay, right? Now here what we can understand, this m by L cube is common, so we can take it out and 2 will multiply to this bracket, and then we'll add this term into this term. So if you do that, then this 2 multiplied by 2, it will be 4b cube, then 2 multiplied by this 2a, so it will be 2a square, and then this bracket plus, since we are adding, so plus this portion, so this portion is equal to 2a cube minus b square in bracket this term, right? So like then what we'll do, we'll cancel out the common term, or we'll add like if the terms are same. So here if you see, it is b cube term, and at end we have got b cube term. So this is positive, this is negative, so it will be 3b cube. So I am writing it here. This is 6 a square b. So there is no a square term now, so this will be as it is. This is we are multiplying inside, so if you multiply inside, this becomes like 2 into 6, and that's how we are getting this term. Minus 2 into this 2a, we will get this term. Now this negative and this positive term will get cancelled, and then we'll get b square term. If you multiply inside, then this will be 3b square a, so 3b square a. So this is what we are getting. Now we will be taking this 3 and b term outside from this one, right? So if you take 3 and b term outside, you will get this equation, b square minus 2a square minus ab. So I am writing equation 3 since I need to substitute later on, so I am giving this equation number 3. But if you like write down this into like bracket multiplication, then it will be a plus b into b minus 2a. Now this is what like equation we get, and this is the equation of MFAB. But we can substitute this a plus b as L, right? We know that a plus b is equal to L. So now I have substituted this as a plus b equal to L. So this L and this L cube will get cancelled, you will get square. So this is the equation that you need to remember. So friction moment at support A is equal to mb by L square in bracket b minus 2a. And this is the equation that we should remember. This is equation number 4 I am writing. And please remember, this equation we got with the sign that moment at point A is clockwise moment, right? So this is the clockwise moment equation, right? Now we'll substitute this equation number 13, since like 3 we cancel, so it is MFAB. So we'll substitute this MFAB equation in say equation number 11, right? We'll substitute that value here. So if you do that, what you will get is 2 MFAB. I am just rewriting those both equation number that 13 and 14 to revise. So equation number 11 is 2 MFAB minus MBA is equal to m by L cube in bracket like minus b square minus a minus b, sorry, 2b cube minus a square in bracket 3b plus a bracket complete. So and then MFAB, that equation number 13, this equation I am rewriting. So mb by L cube in bracket b square minus 2a square minus ab, right? So we'll substitute this equation like equation of this MFAB here in this equation. So this is what we'll get. So like again, what you do, you can rearrange the term. You bring this like MFB on right hand side, or say you keep it on this side and you bring this term on other side and then make it positive. So if you rearrange this like equation 11, then this is what we'll get. MFBA, this is positive since like you put it on this side or this side and bring it on other side. So it is just like rearrange the terms. So MFBA is equal to 2 MF. So MFAB minus this like value, right? So again we'll substitute now value of MFAB. So if you substitute MFAB here, and then we can take this m and L cube outside, so remaining terms will be like this. B again this 2 we have to multiply inside, so this will be 2b square minus 4a square minus 2ab minus, since we have this minus side and we have taken only m by L cube outside, so this minus we have to multiply inside. So this will be minus b cube, this minus minus plus a square, right? And then plus a square will be multiplied inside. So if you multiply plus a square, it will be 3a square b and plus 3a cube. So this is like what we get. Now we will add or subtract like a similar power term. So this 2b cube, and here we get minus 2b cube. So they'll get cancelled. Here a square term, here a square term b, a square b term. So this is minus, this is plus, so remaining will be a square b term only, 4 minus 3. Then remaining these two terms will be as it is. So from here I am getting minus a square b, then this term as it is, and then this last term will be there. Now you rearrange the term, and then if you write down again in terms of like bracket, so we'll get this 2 bracket a plus b in bracket a minus 2b. So now this a plus b we already know it is L, so this L square L cube will get cancelled and you will get square term. So finally what we get, MFBA is equal to MA L square in bracket a minus 2b, right? This is clockwise moment, right? This time this is what we have assumed at the beginning. These two moments are like this. Sorry, this moment is like this. This is what we have assumed at the beginning. If you remember, this is what assumption we started with. So this moment is this direction. So no doubt, like in general, like we write down this moment at MFBA in say anti-clockwise notation. This is what we generally write down. So if you want to write it in this fashion, then you should make it 2a minus b, because many people they write it in this way and they write 2a minus b, or otherwise if you are using this sign convention what we have got, then it will be b minus 2a. This portion will be as it is, just like putting minus side outside, right? So that's how, like either you remember this one, or this one and this one, right? This is how you can calculate the fixed end moment. Like again, reaction, remaining reaction you can calculate using equilibrium condition. This two vertical reaction here you can calculate using equilibrium condition, right? And then you can plot shear force and bending moment diagram. So we have already discussed that calculating shear force is as normal as like a normal problem, but calculating bending moment, what we do, we plot this bending moment due to this fixed end separately, and then because of this load we plot separately, and then we overlap, right? So anyway, we'll solve some numerical that time. We'll see how we can plot shear force bending moment diagram. Now next, this is the last case. So next case is that if the support sinks down, or settles down, then what will be the moment? So again you understand, if like say support B is sinking down or settling by value delta, right? So if you see like in release structure, we can understand the rotation here will be clockwise rotation. So to resist this clockwise rotation, this moment will be in anti-clockwise direction, whereas here the rotation will be clockwise. So to resist this clockwise rotation, fixed moment will develop in anti-clockwise direction. So that's how I have given this two direction. This is like a clockwise moment at MFAB, and this is anti-clockwise moment at B point, that is MFBA, right? So again procedure is same. First we will release this two, right? So release these two moments and static indeterminance is 2. So if you release and if you give this settlement, then beam simply it will deform like this, right? So it will simply like deflect by this, and this deflection is like delta, right? So we are there, we applied the load. Here since we do not have a load but we have settlement, so on release beam we are giving that settlement. So if you apply this settlement, then here you will get theta A, here you will get theta B. Now if this is delta and this length is L, what will be theta A? Then it should be equal to like L delta by L, right? Theta is equal to delta by L. That will substitute little later, and then we'll apply this fixed end moment, right? If you remember in previous case, this moment was like opposite in nature, and this was opposite to that. Here also it is opposite, but this is clockwise movement, it is anti-clockwise movement. In previous problem it was clockwise movement and this was this was anti-clockwise and this was clockwise movement. Again, one more thing, so that is like case. Now again we have to add this 3, and actual rotation here in the problem is 0. Here it is 0. So using consistency condition, we can say that addition of this 3 should be 0. This one, and this one. So we have written it here, right? So again, this is clockwise rotation, this is anti-clockwise rotation, this is clockwise rotation. So clockwise will get add, anti-clockwise will be minus. So clockwise positive sign, anti-clockwise negative. Here this is clockwise, this is clockwise, this is anti-clockwise. So anti-clockwise we are putting minus. So either way you can write, you can assume anti-clockwise positive, then also you'll get the same equation. So this is the equation we got. Now we'll substitute value. Now here as such we do not need to calculate, do not need to use a conjugate beam to calculate theta A and theta B. It is from the geometry itself we can get. So theta A equal to theta B will be delta by L, and we already know how to calculate theta A and theta B. So like I'm writing it directly. So now we will be substituting this value in this consistency condition. So we have substituted this into consistency condition. So once you substitute in the consistency condition, just like here we'll be again adding, we have subtracted. So subtracting this 2, and then what will get this condition, what it tells, like it is very simple. Like if you take a minus, then this term will get cancelled, this become plus, this become minus, right? So that's how, if you rearrange the term, and then easily you can prove that this 2 moment should be equal, right? And that is but obvious also, since there is no any other moment. So this 2 moment must be equal, then only beam will be in equilibrium. So this is like the derivation that we get. After that, like we'll substitute this MF AB equal to MF BA in any one of this equation. Sorry, this either you substitute here or you substitute here, and like we'll get the answer. So I'm substituting it in equation number 1. So this, like I'm substituting this MFBA instead of MFBA, I'll be writing MFAB now. So this is what this is the equation that I have. So I have substituted MFBA since they are equal. So MFAB. And if you rearrange this term easily, what we can get is MFAB equal to 6 EI delta by L square, which is also equal to MFBA. So this is the equation that we get because of settlement of support, fixed end moment that we get. Remaining procedure of calculating shear force bending moment diagram, we'll discuss it in numerical problem. But what I suggest, this table you should remember, because if you in problem directly numerical values are given, then no need to derive this all result. So this result directly you can use and you can plot shear force bending moment diagram. So I am just summarizing this, like this is the like 4 cases that we have derived. First, due to UDL, so fixed end moment, here it will be anti-clockwise moment, here clockwise moment, and both will have the magnitude equal to WL square by 12. Then for second case, if there is a centric load and like you have a moment of MFAB, this is again anti-clockwise, this will be clockwise, and the value will be here both values are different but they look similar. So WA square by L square. So when you are calculating moment at this point, that time you have to take a square term of B side, and when you are calculating moment at A point, that time A terms you have to take a square. But this sign convention and these values are fixed, right? So if you are changing the like sign convention, instead of like say here we are assuming, instead of say anti-clockwise, if you are showing it clockwise, then this will be negative, right? Now this is important case, like here, like I have shown this moment with traditional way, both, since we are writing all like clockwise, anti-clockwise, so all B portion it is like a clockwise moment, and at A point it is anti-clockwise. So this will be MFB equal to MB into 2A minus B, and MFB is equal to MA by L square A minus 2B. Right? This is what we have derived. So this you can use, or maybe what you can write is, this is what we have derived, right? That is what I told. Either you can write down this in this way, so that time it will be B minus 2A, but if you are writing in this way, then it will be 2A minus B. So I am writing it in anti-clockwise, so that's how. Otherwise, if you are comfortable with this sign, you can use like anti-clockwise notation for this moment, fixed moment at A point, and then this will be B minus 2A, like this, right? So that way also you can remember. Now for settlement, again here this applied moment we are assuming a clockwise moment. If it is anti-clockwise, then this sign will get opposite, right? So like what I am telling, if my moment is acting like this, anti-clockwise moment, then here the moment the moment that will develop is like this. So you just remember the direction in which this moment acts, this two moment will be same. Like if my moment is acting in this direction, so this two moment will also be in this direction. So all moment like will be having the same notation. And if you are like using this sign convention, then the value will be MFAB is equal to MB by L square into B minus 2A, and this MFBA is equal to MA by L square A minus 2B, right? So either you assume this sign convention, like even if you use like if your problem has this load, then also this value will remain this only sign convention will get changed, right? So what you have to remember, instead of like remembering this equation, better you remember this equation, because there is less confusion about sign convention. So like if applied moment is in clockwise direction, then the fixed moment will also be in clockwise direction. If applied moment is anti-clockwise, then this fixed moment will also be in anti-clockwise direction, and the equations will look like this. So even for this both problem, this value will be remain same. So that is what. And then finally the settlement of support. So like here if B support is settling down, then this will be anti-clockwise moment, clockwise moment, anti-clockwise moment, and this will also be anti-clockwise moment, right? Whereas like if A support is settling down, then moment will opposite. So this will be clockwise, this will also be clockwise, and we know that the magnitude is will be same at both the end, and which is equal to 6EI by L square into delta, right? So that is what. So this is the end of the class. Next time we'll solve one or two numerical. Simply it is like substituting this value, and then we'll move to the next topic. Thank you.